Hi guys, good morning. Last week we looked at the pressure distribution in a static fluid and we concluded the chapter. However, let us recall a couple of important points from that chapter. If we have an incompressible liquid, that is, the density is a constant, then at a depth of h, the hydrostatic pressure is rho gh. However, if the density of the liquid varies with the height, then we have to go to the differential equations in order to find the hydrostatic pressure. Now let us keep these important points in our mind to move to our today's session on static forces on submerged surfaces. Now see, still we are looking at the static liquids. We are not looking at the dynamic or moving liquids. We are just looking at the stationary liquids. Now, the learning outcome from this session would be, how can we find the static forces on submerged surfaces, and what are the applications of these static forces on civil engineering structures. Let us forget about these liquids for the time being. Now, how did you find pressure at your high schools? We say pressure P is equal to the force F divided by area A, where this area A is the perpendicular area to the applied force F. So that gives us the force is equal to pressure into area. So let us start our today's session from there. Let us consider a plane object which is say under a liquid submerged, and assume the total area of this object is A, and we'll consider and say small area of delta A1. If the hydrostatic pressure acting on this delta A1 is P1, then the induced force due to pressure on this delta A1 is P1 delta A1. Similarly, the induced pressure force on delta A2 is P2 delta A2, where P2 is the hydrostatic pressure on delta A2. Similarly, we can find number of small forces like Pi delta Ai throughout the area of A. Now, if I ask you to find the total area of this A using delta A's, what would you do? You just simply add these things together. Can we do the same thing in order to find the resultant force of these small pressure forces? See, P1 delta A1, P2 delta A2, and so on. Yep, we can do the same. But remember, force is a vector. It has a magnitude and the direction. Therefore, we need to add these forces, small forces, not only numerically, but also considering the direction. Now, let us again forget about these this liquid thing. Now, we have a set of forces, say P1 delta A1, P2 delta A2, Pn delta An. And we know how to find the resultant force out of this set of forces. But what are the important points of this resultant force? Obviously, the magnitude of the resultant force, the direction of the resultant force and the point of action of the resultant force. So we have to put all these three even in the liquids in order to find the hydrostatic pressure force acting on the submerged surfaces. So we need the magnitude of the hydrostatic pressure force, we need the direction of that resultant force, and we need the point where the force can be considered to act. That is the center of pressure. In order to find that, let us consider a couple of simple examples. Say the left hand side figure shows us a vertical tank wall, say which is under a boat, and we know since it is water and we can assume it to be an incompressible liquid, the pressure variation along the depth is a triangle. So if the depth of the vertical wall tank is h, then we know the pressure at the bottom is rho gh. Now we can complicate this thing a little bit by inclining the wall to the right hand figure. Still, the pressure distribution is a triangular distribution, and at the bottom the pressure can be considered to be rho gh if the vertical depth from the free surface to the bottom of the tank is h. Now we need to find this resultant force F, direction of that F, and center of pressure. Okay guys, the direction is quite obvious, isn't it? Because we know pressure forces are applied perpendicular to the surface. So it's automatically given. Still we need two important points, that is the magnitude and the center of pressure. In order to find these two, let us consider the simplest case. It's the vertical tank wall. Let us assume the water depth is d to the bottom of the tank and the width of the tank is b. First, we draw a constant depth contour at a depth of y from the free surface. Then we give an area of delta A to the contour by increasing the thickness of the contour to delta y. So what is our delta A? Delta A is equal to B delta y. Now, next we calculate the hydrostatic pressure force delta F acting on this strip. How do we calculate the hydrostatic pressure force on this strip? It's the pressure on this strip into the area. Now the pressure acting on this strip is rho gy, and it's a uniform distribution. Why? Because we are in a contour and at the same level we have the same pressure conditions for the same liquid. That's the level rule. So our delta F is rho gy delta A, which is equal to rho gy b delta y. Now if I need to find the total force due to this BD area, what would we do? We would sum up all these small areas from free surface to the bottom of the tank. That means from 0 to D. Mathematically we can do this thing using integration. Now let us do this simple integration. So the total resultant force F is equal to the integration from 0 to D delta F. That is, delta F is rho gy bd. Why? From 0 to D. So this is an incompressible liquid. So we can consider the density is a constant, gravitational acceleration is a constant. It's a rectangular ball, so b is a constant. So we can take these rho gb outside the integration. So we are ending at integration from 0 to d y dy. Now, is this familiar to you? Y dy, integration of y dy. Let us put this b inside this dy. B dy. What is that? It is dA, isn't it? Integration of y dA. That is the first moment of area, isn't it? Which you have used in your high school physics and so on. Now, if we do the integration, simple integration, we end up at half rho GBD squared. Now, that is the magnitude of the resultant force. Can we prove this one? Yeah, it's simple, isn't it? See, now we started with a triangular distribution of pressure starting from 0 to rho GD. That's a triangular variation. So how can we transform this triangular variation to a uniform distribution? It's simply the average, isn't it? So we have 0 to rho GD. That's the triangular. So the uniform is half rho GD applied on the total area BD. So our induced force is half rho GD into BD, ending up with the same answer. Now we know 2 points out of 3. The direction of the resultant force and the magnitude of the resultant force. Now guys, sometimes we present this magnitude of the resultant force per unit width. It's easy. You just divide this half rho GBD squared using B, and you ending up with F is equal to half rho GD squared. That's per unit width. Sometimes this form is important when you go to the real world examples like dams and so on. Okay, still we need one important point to find. That is the point of action. Now, in order to find that point of action, we use the basic techniques, which you have even used in your high school physics when you were looking at the location of gravitational center of various objects. So we take the moment. Okay, guys, what do we mean by moment? It is the force into the perpendicular distance from a concerned point. Now, if you look at the moment from this delta F force over the free surface, it's gonna be delta F into Y. Now we can say delta M is equal to Y delta F. What is delta F? It is the pressure force, hydrostatic pressure force, which is equal to the pressure rho G Y, then area B delta Y, into the perpendicular distance of Y. That gives us rho G B Y squared delta Y. Now, if we need to find the total moment of the these small forces across the free surface, what would we do? We again do a simple integration. That is, M is equal to integration from 0 to D, that is from free surface to the bottom of the tank, of delta M. Now delta M is rho G B Y squared delta Y. So we know rho G B are constant, so we can take those outside the integration, and we are ending at integration from 0 to D Y squared dy. Again, is this familiar to you? Integration of Y squared dy. Just put this b inside this dy. It's the dA, isn't it? Area. Now we have y squared dA and integration of that. That is, yeah, that's the second moment of area. Okay, if you are not that much familiar on second moment of area, don't worry, because in the coming lectures we'll be looking at the second moment of area, parallel axis theorem, various objects, various shapes, into the depth. So don't worry for the time being. Now, if you do this simple integration again, we'll find the total moment generated due to these small delta F forces is 1/3 of rho g b d cube. Now we know that should be equal to the resultant force into the distance from the free surface to the resultant force, that is Fyp. Fyp should be equal to m. So that gives us 1/3 of rho g b d cube is equal to half rho g b d squared by p, and gives us Yp is equal to 2/3 of d from the free surface. Can you prove this again, guys? Yep. Now we started with triangular distribution. What is the centroid of the triangular distribution? It is 2/3 of the height from the top, isn't it? So now we have found all three important points: magnitude of the resultant force, then the direction of the resultant force, then the location or the point of action of this resultant force. However, we know this is the simplest case where we can find. But as engineers, we do have to cater much complicated problems in real world. Say irregular object, curved surfaces, inclined surfaces, and so on. Therefore, our next discussion is going to be to obtain a set of generic equations, find out the hydrostatic pressure force on a plane surface but inclined. And finally, we'll extend our discussion to find out the hydrostatic pressure forces on curved submerged surfaces. Let us recall the learning outcomes of today's session. We started with in finding the hydrostatic pressure force. Then we looked at a simple example, probably the most, the simplest example. Then we found out the magnitude of the resultant force, direction of the resultant force, and the location of the resultant force. Okay, by the way, why do we have to find these hydrostatic forces? What is the real reason? Okay, that is something you can think until we meet in the next class. A clue may be, think about dams, spillways like Three Georges Dam, and so on. Okay guys, until we meet on next Monday, have a good weekend. Thank you very much guys.